So this is a little bit of help with the student activity, modeling with sinusoidal functions. So what we're going to do is start looking at some sine and cosine curves. Part 1, we are going to write mathematical equations of sinusoids. The following sinusoid is plotted below. Complete the following steps to model the curve using the cosine function. So we have to remember that this curve is cosine. So part A, what is the phase shift? The phase shift is where you move left or right. So we're looking for the maximum, and usually the maximum passes through the y-axis, but our maximum's right here. So how far to the right did it go? And you want to count your boxes. 1, 2, 3, 4, 5, 6. So we are using h equals 6 for the cosine curve. What is the vertical shift of this curve? We have a formula for that, where we take k is equal to your y max plus your y min over 2. So for us, our y max is at -16 right here, and our y min is at -26 divided by 2. So we have really plus 26 minus 16. No, wait, this is a plus, sorry. So -42 over 2 means that k is equal to -21. All right. Letter C, what is the amplitude of this curve? That's how high it goes. So for this, our amplitude is equal to the absolute value of your y max minus your y min over 2. In this case, it's -16 minus a -26 all over 2. The numerator becomes 10, the denominator still 2, so this is equal to 5. Your amplitude is 5. Letter B, what is the period and frequency factor of this curve? Sorry, this is letter D, but define B. So the period is how long it takes, and that's equal to 16. And in order to find your frequency factor B, you're going to have 2 x max minus x min. And just to remind you, x max and x min. So here's a maximum, here's the minimum. We're going to use that as kind of one, this distance, that's what I'm trying to say. And with the 2 in front of it, it's actually going to double it and give you an entire wavelength. So we are going to do this, which becomes 2 times the quantity 6 minus a -2. 6 minus a -2 is 8, so 2 times 8 is 16. Then 16 is equal to 2 pi over b. Wavelength, a normal wavelength would be 2 pi. Over b is what we're looking for, and ours takes 16. So if we solve for b, b is 2 pi over 16, or pi over 8. And that's the frequency factor. So letter E, sorry that this goes on to another page. Write an equation using the cosine function that models this data. So basically we have to put everything together. So we're going to say that y is equal to 5. That was the amplitude. Cosine, your period factor is pi over 8. And then that shift is x minus 6 minus 21. You could write this for anything that shifts it like a whole nother 2 pi to the left or the right, but we don't want to do that. This is what we got. All right. Number 2, the following points are a minimum and a maximum of a sinusoid. Complete the following steps to model the curve using the sine function this time. So same idea, but they didn't give us a picture this time. So K for your vertical shift. What is the vertical shift of this curve? I don't know why they put a D here. I'm thinking that should be a K. Anyway, K is equal to your 2 y values added divided by 2. So this is 24 over 2, which is 12. So k equals 12. What is the amplitude of this curve? This time we subtract that max and the min, and you want the absolute value of it divided by 2. So 20 over 2 is equal to 10. Your amplitude is 10. What is the period and frequency factor? So the period, and we take the x values of that max and min again, times 2 is going to be 4.5 minus 1.5. This is 2 times 3, which is 6. 6 is equal to 2 pi over b. These look the same, don't they? So b equals 2 pi over 6, which is equal to pi over 3. And then again, put it all together, write the equation. Y equals, the amplitude comes in front, that's 10. Sine function, x over 3. Nope, that's not an x, is it? It's pi over 3. Yikes. X. This one does not have a phase shift, so you don't have to add or subtract the x. And then plus 12. That's where it shifted up, our vertical shift. All right, that's all part 1. Part 2, model real-world problems using sinusoids. The average monthly temperatures for Phoenix, Arizona from the years 1981 to 2010 are shown in the table below, with value 1 representing the month of January and the value of 12 representing the month of December. Complete the following steps to model the curve using the sine function. So if you look at your values, they start at 69, they go up to 104, and they come back to 67. So we have all these data points that go up and come back down. We're going to use those to create a sine function. Now, this part, for part A, you want to make a scatter plot of the data, use the grid below to include a screenshot. I recommend going to Desmos. You can go to desmos.com, or there's an app, but you can go through and put in the ordered pairs, or you can make a table. You can Google how to make a table in Desmos, and it'll do a pretty nice job for you. But you'll have something that looks like this when you're all done. Again, not perfect, but head to Desmos to make that. So letter B. Oh, there it is right there. You can plot it on this. Never mind. Etc. etc. So you can plot your points. They kind of look like that. What is the minimum temperature in the data set? You don't really need me for that, but you know that the minimum is 67. What is the maximum in the data set? The maximum is 106. What is the vertical shift? Again, let's use D, or other notes have K for the data set. So that's where we add your max and min and divide by 2. So 67 plus 106 divided by 2 is 173 divided by 2, which is 86.5. What is the amplitude for the data set? This is the one where we subtract them and take the absolute value. So 106 minus 67 over 2. So this is 39 over 2, which is 19.5. What is the period and the frequency factor for this set? So the period is 12, because we have 12 months. And the frequency factor is, what did we say? 12 equals 2 pi over b. So b is 2 pi over 12. So b is pi over 6. What is the phase shift? The month closest to the average temperature is April. So the phase shift is approximately 4. That one you kind of have to eyeball a little bit. That's a little tougher to see. $86.5. Okay, so where does that come from? Your vertical shift is here, your 86.5. So if we go back up into the table, this value is closest to 86.5. So that's why we're going with 4. Because 4 is the month that aligns with that. write an equation using the sine function that models this data set. So when we put it all together, y is equal to 19.5 sine pi over 6 times x minus 4 plus that vertical shift 86.5. Good. When would you expect the temperature to be 82? Well, you can go back to your graph. So if y equals 82, then x would be this or this. You can set this equation equal to 82, this one up here. That'd be the most precise way to do it. And then use your calculator to solve if you have practice with that in your graphing calculator. If not, you could come up here to your graph. So we want 82. So pretend you had this whole graph. You can come over here to 82 degrees and tell me, all right, where on the graph here and here, it's equal to 82. I got a 3.5 and a 10.5. Not too bad. I'm going to scooch those dots over a little bit. So 3.5, we have January, February, March, April. So halfway through March. And then the 10th month is October and the 11th month is November. So we would say mid-March and mid-October. Mid-March, mid-October. All right, excellent. Number 2, in the real world, humans hear sound as an analog signal. This means the signal is a continuous waveform, which is completely processable by human ears. However, machines hear sound a little differently as they process sound digitally, which is a discrete waveform. When sound is recorded or transmitted electronically, the continuous analog waveform is sampled to convert it to a discrete digital sequence. Sampling is the process of reducing a continuous time signal to a discrete time signal. As the sampling rate increases, the sound quality of the recording or transmission will improve. The graphs below represent 2 different samples of a pure tone. Sample 1 is taken 8 times per unit of time, and sample 2 is taken 16 times per unit of time. So we don't have to create anything here, but we're just gonna talk about these. Why would sample 2 produce a better replication of the pure signal? There's no exact right or wrong answer here, but you just kind of want to justify why it would be better. And the answer I have is sample 2 will produce a better model because it has more data points that can recreate the curve accurately. And that's true. And it's kind of the same thing that happens with your high def television or any technology that gets better and better. You have more data points. So music was MP3s and then, MP4s. If you have more data points in there, it's a more clear sound. In the TV, if you have more pixels in your TV, it's a much better picture. And I know pixels don't even happen anymore. So for this one, we could say more data points result in a better model. However you want to word that, but the big idea is you have more data points. Write a sinusoid model for sample 2. Now, they didn't give you all the steps like they did in the first few, but you go through the process. You can see that your amplitude is 7.9. Your B for that frequency phase is 8 underneath pi, so pi over 8. X minus 0.8, that 0.8 is the phase shift, and then plus 8 is how high it shifted up. So for letter B, you'd have to go through all those steps and calculate the different pieces just like we did prior. So I hope that helps, and good luck.